sense is like, now I could also view that I have one set of observation, like you look at my lips, and then you also have the audio. So you look at my lips, you look at the audio, and what generates this? And so you say the audio is generating, there is some latent representation that is generating the audio, maybe some kind of phoneme state, and maybe there's some viseme states, and maybe you say, and that's a design decision, you say phoneme is really the one generating the viseme. I want to pronounce something like a phoneme, and so just to pronounce it, I need to shape my mouth in a certain way. And so in this case, I have dependence this way. So this is the Boltzmann zipper. We'll talk about Boltzmann machines in a little bit, but this is the Boltzmann zipper. It's because the Boltzmann machine, and then extension of that was the Boltzmann zipper. And now you also have what's called the coupled HMN. It's an advantage over the zipper, more flexible, because neither vision nor sound are privileged. Both of them depend on the previous. So VT depend on HT, and HT plus depends on VT. So it is coupled in that sense. Instead of making it direct this way, it's coupled. And then you could ask yourself, if you remember, the multimodal LSTM was inspired with this, is that you can have how much coupling do you want? How much does H really impact VT? How much of V impact H? And how much VT plus 1 depend on VT? These are parameters that I think they were called alpha and beta in the multimodal LSTM. So I wanted to give you some intuition. If you look at the nice news also is, the good news is that there's a lot of Python libraries that are there to easily implement these models and optimize them. And we'll talk a little bit more about optimization next week. I want to also talk in the last part of the lecture today about generating data, because what's really nice here is that I could also maybe eventually with this, given the seed, generate data, or I could maybe have with the beginning start generating the rest of the sentence. And so, but we also there's a family of models in neural network architectures that are also designed for generating data. And some of them will model the joint distribution. And so in that sense, they are generative model in the sense of generative versus discriminative, because they also model joint. Some of them may or may not have modeling explicitly of the joint distribution, but the community started calling them generative neural model anyway, even though maybe they don't model the joint distribution. So the terminology, most people will follow, but some authors will use the term generative, even though it's not modeling the joint distribution. I can't do anything about that, but let's just want to let you know about these terminology. So based on what we've studied up to now, and I say, I want to learn a generative model. I want to be able to generate sentences. And let's say for a second, because a lot of you are probably right away jumping to transformer and BERT and all this. So maybe earlier than that, before BERT and all this, what would be an interesting way? And one way to learn an encoder is to learn to train a decoder. So the idea here of the autoencoder is I take an image, I bring it to a latent space, like hopefully usually much smaller in dimension than the input, and I then have the decoder trying to recreate this input. And so this is this could be something that I could train, and then I could imagine dropping the encoder and then just going around, and or what I think I could do is encode an image and then start messing around my Z. Like I encode a cat and I start like adding either like adding to it to go, maybe I would like to morph it to a dog. Let's say I take the image of a cat, I get the Z, I get the image of a dog, I get another Z, I get those two Z, and I'd like to morph from one to another. And in theory, I could just like linearly interpolate between these two and then start synthesizing a morphing between the two. This is, in theory, I may be able to do that. In practice, the latent space, if you were to do a TSNE on it, you would see, and you've probably seen it yourself when you plotted, those TSNE, if you just use like typical neural networks, often they're very clustered. They're very clustered, and they don't, there's space in this that just have like very underrepresented by the training data. And so that's an issue, because suddenly this latent space is not really good for generative, because what it means for generation, for generating, because suddenly I cannot warp between 2 points, because I may be unlucky, I may be in 2 different clusters that have nothing, no representation from the training data in between. So how can I solve this? There's been a line of research, which we'll discuss also more next week, on this, of like, how do I can make sure that I can interpolate in my Z space. And the idea, the intuition is I'm gonna parameterize, I'm gonna put a constraint here so that instead of being always clustered, and that's really bad, because if things end up getting like in different part of the space, I'm gonna force it to follow a normal distribution. Okay, and by forcing Z, so if I take all my training sample and I project them in a Z space, I'm gonna force that these projected samples to follow a distribution, and usually I will pick like a normal distribution. And so I will emphasize, and so Z itself also, I'm gonna make it parameterize as a normal, as a Gaussian probability distribution. So, and so I will say all of this data can be, I can parameterize this data into a space which is parameterized with a multivariate Gaussian with a mean and a standard deviation over it. And so I will have my encoder and I have my decoder, and then I will enforce that this normal distribution, if I don't enforce it, it could end up, if I don't enforce anything, if I remove this part, then I just reparameterize my Z, but that doesn't gain me this issue. I could still end up with different different part of the space, but I'm gonna force it to follow a normal distribution, and there is different way you could force it. One way that was shown to be working well is to encourage, like with the KL loss, to be able to encourage the Z to follow a normal distribution. As I mentioned, will be more details about it, about variational approaches. We'll have a full lecture about variational, because there's a lot of very interesting extensions on variational autoencoder. But when you do this, then suddenly this normal distribution has nice property, because I can warp. I can take 2 images, like 2Z, I can warp between that. I can move around. And I know that wherever I move, with, as long as I'm within that Gaussian, that I will be a valid, or at least something that's been seen in the training data. But one issue is that they don't look realistic. I mean, they kind of, but they like they don't look like this image of me, and so they don't look full realistic. You know, they've been generated. And so this is this really interesting approach that was suggested to extend that says, like, hey, I have a generator, and maybe that generator has an autoencoder, so it's an encoder, and then you have a random vector, and then you're generating. And we'll see some of these. But so I have my Z in a random vector, and I want to synthesize an image, but I want to synthesize image to look real. And so what will I do? I will say, I'm going to randomly, once in a while, give a real image and sometimes a synthesized, and I'm going to train a discriminator to know if it's real or fake. And what's nice is that the generator is trained to map any random vector, and that's and so I talk in the variational autoencoder where you're trying to force it to be Gaussian. But for now, let's say we don't put any of these constraints for now, and I'm back to the point where I take any random vector, or it's random vector maybe from a certain distribution, but any random vector from a certain distribution, and then I generate it so that any image I generate looks real. I want that I give it any vector, and it should give me a real image, an image to the point that is, if I have like the, and as you can see, they're going to compete with each other, but train to map any vector to an image, and then the other one is to train to distinguish synthesized image from real image. And so how do we train both generator and discriminator? So the idea here is that you will have a term. So here you have the expected value. So you want, for all of the data that comes from real image, you want your discriminator to be as successful as possible. And so that your loss will make it, you want it to be as successful as possible. And then when you, and then the opposite, and so if it comes in synthesized, it's 1 minus D. You want to be sure that, and depending, it's real and fake. Like, and so depending if the D output is real or the output is fake, like this would be D or 1 minus D. It's just depending on what you call real and what you call fake. But yeah, one of them, when the discriminator says real, it should be real, and when it says fake, it should be 1 minus D, so it should be from this data. That's if you wanted the discriminator to succeed, but you also want the discriminator, so it's a min-max in this case. So because you want, at the end, you want to minimize the generator while at the same time maximizing the discriminator. So the generator wants to make this as small as possible. The discriminator wants to make this as high as possible. And so one way to optimize it will be to fix the generator, make the discriminator as high as possible, or fix the discriminator and make the generator as high as possible. So that's one way to generate, to optimize this. Now, GAN in itself is useful, is somewhat useful, but I personally like even more conditional GAN. Conditional GAN is interesting because it's not only that you're like able to generate any image of a cat, let's say, because let's say the real images are all of cats. But now maybe I have also the possibility that I have an external or another random variable that I will be able to use to start to gear the generation. And there are different variation of like different ways to implement a conditional GAN. But the general idea here is the same, is that you learn to synthesize the image, but condition on the class. And the challenge will be to be sure that it has been conditioned. Because if you just take this and just add this variable here and just go ahead, there's a chance that it just ignores it. And it's possible that it completely ignores, the generator completely ignore. So one way to be sure that it is done correctly is train to distinguish, to synthesize real image, condition on the image class also. So you could make also the discriminator. But here you're conditioning one, and so that's one way to do it. One way that was really interesting is so it's a bit almost like a cyclic loss, as a way is like you want to be sure the discriminator, or at least the discriminator wants to also get the class, and that part you want it. It's not going to be part of the adversarial part, is that you want to be sure that you also output correctly the decision about the class. So your discriminator is trying to do real and fake, and for that you will have the loss we talk about. But for this one, we'll have a more classic one to be sure that your discriminator is able to discriminate the class. So you want to be sure that if you put a cat here, you get an image of a cat. If it's a dog, it's an image of a dog, because the discriminator will be able to do that. But what if we would like to also learn to encode from X to Z? So this is the decoder, but maybe we also want to encode from X to Z. And I'm going to give example in a little bit about this. I'm going to give you models about this, but before I go into that, I want to give you some examples of these models, like the Infogan. And so one of them is audio to scene. So you get an audio, and then so the conditioning is based on the audio. And it's still the random class, the random noise here. You have your generator, and your discriminator will discriminate, but you kind of have a second discriminator. Could be it's kind of, you could call it the same discriminator, but just a multitask. One is about fake versus not fake, but the other one is about predicting. So it's a nice simple extension. So it's not exactly the same architecture. It's not the same class. But here in this one is you have a different conditioning that is different from the class, but they're related. In fact, in this case, there is a link between my audio to that class as well. There's a link between my audio to that class. And so that's interesting, because now they can do some really cool things. I hope you can hear it. Here is a sound.
Do this.
And the system automatically, just from the sound and a bunch of paired data, managed to I'm saying both at the same time. Sorry on that. I need to work on this. I will just click this way. But you get the, in this case, it's going to be playing. What's really nice is like, it's both of them are water, all four of them are water, but a little bit louder. So it's just a little bit, so it's a small, but then if it's really loud, so it was a little trick that was cute. One that's related also to our current research in my group is also talking head, where the input in this case will be of the generators will be the landmark, and then you get the synthesized, that's your goal, and then you have the discriminator, the same discriminator, real or fake, and then so you have the ground truth, and what they added to that is also looking at the image to help with this, looking at the input image as well. But this is interesting because now they can do this and also customize. So what the input will be is that you get some landmark, you get an image, and you're generating that image. So you're conditioning almost on two things. They are like the landmark, and you want to generate the image based on this. So you will, and so it may be an image of a different person, and you want them with having the same facial expression as well. And so you get some things like this, which is, I think, really, really cool. taking that input image and making her talk, which that was really cool to me. And then one last thing is the idea of also bringing the which I mentioned earlier, is like, what if you would not want to just create a generator, but you would like to have an encoder, like you would like to go to be able from X to Z. And then what you can do, and one approach that was done, is they call it the bidirectional GAN. And so this gets a little bit confusing, but the discriminator will have to do kind of two discrimination tasks. It's like saying, is the image real or not, and is the encoding real or not? Is it a real encoding, or is it fake encoding, or produce encoding, let's say generating encoding, or is it a synthesized image or a real image? So is it a real vector or a synthesized vector? And so it's a doubled one. So you kind of select between this and this learn to map one. And finally, the final family that I want to talk about is bringing the autoencoder. So it's another way of generating, because it brings like the autoencoder. So you encode to something and then you generate. And then so it's a way to train your autoencoder. And as you know, you can make it a variational approach of that. And that's really nice, because a lot of this work on paired data, but now you can also extend this kind of architecture to work on unpaired data. Unpaired, like, or weakly paired. It's still paired up to a certain point, like you know that there's some relationship, but you don't know which one is with which. And for that, I think there were more details about this next week, but we'll talk about these cycle GAN as a way to approach this, to do this. I'm not going to go into details now because of time, but the idea of the cycle GAN is to say I have one modality, I have another modality, but I don't know which image is really matched to which in the other modality. I don't know which one are matched together. And so what I will do is I will use the cycle loss. I will say, for that modality, that sample I have, let me try to produce it in such a way that I generate it. And the same way I had the temporal consistency, you know, we had that for the cycle temporal consistency. I can use that and say any image from modality 1, if I generate them, it should be close to each other. And then I will be doing the same for the other modality. Any sample I have, I generate it in the other modality, and that should be, and I want them to be close to each other. So this cycle consistency loss that we saw for temporal can also be used that. And there was this beautiful paper that put everything together, bicycle GAN, and they were able to do really cool things by putting everything together, taking the sketch and being able to generate in a different sample. So more details on this next week. I want to start this discussion about generative models and also discuss about probabilistic graphical models. Thank you very much for your attention.